Welcome to E-Pathshala lecture series in computer science, and this course is on operating systems. And today we will learn about what system calls are and the different structures of the different operating systems. So, this objectives of this course is to understand what system calls are, to learn about the different types of system calls, and to learn about the different types of operating system structures. So, what do you mean by system calls? We learned about what operating systems are or what are the functions of an operating system. And now, the users who use the operating system need to have an interface between the programs that they write and the actual operating system. So, the system calls actually act as an interface between the application programs that the users write and the operating system. So, earlier these system calls used to be available as assembly language programs or assembly language instructions, but now in some high level languages these are available as calls or function calls, where like function calls you have calls that are available for system calls. So, these look very similar to the predefined function calls that you have in high level programs. So, in case of Unix operating system, the system calls can be invoked directly from a C or a C++ program. In certain other operating systems, they can be like library function which in turn can call the system call, or in case of Windows platforms they are part of the Win32 API. So, if you look at a program, say for example, you take a program that is needed to copy the contents of one file to another file. So, you write a program for that, say. So, what will you do? You first try to get the input of the file names, that is the source and the target, that is a file from which you copy and the file into which you write. So, you need the input of these two file names. So, you will try to print a statement saying, say for example, if it is in C, you will say printf enter the name of the source file, then you will say scanf file name, then you will say printf enter the name of the destination file, and then you will say file name, and so on. So, each of these calls, that is the printf, the scanf, in turn will call a system call for its operation, and once you get the file name, then you will try to open the existing file or the original file, and this opening of the file is again another system call. And then what you do? You will try to read the contents of the original file, and this reading of the contents is again another system call. And then maybe you will try to write into the destination file, writing is a system call, and so on. Finally, after reading and writing, say multiple reads and writes, you will close the files, maybe the input as well as the output files. Closing of the files is again system calls. Then maybe you will print a message onto the screen. Printing the message onto the screen is again another system call. Okay. So, here you can see that in the small program where you are trying to copy the contents from the source to the destination, there are a number of system calls that have been used. So, system calls are very important for any program. So, this is basically because this user, when he writes a program, he can't directly access the code of the operating system. So, using system calls, you can actually access the code of the operating system and make use of that. So, how is this actually made possible? So, corresponding to each and every system call, there is something called a system call number, and there is a table that is being maintained in the operating system corresponding to all these system calls. And when this number is given, that number is used as an index into the table in the operating system, and you find out what is the actual routine within the kernel that needs to be invoked for this, and that routine is invoked and that is executed. Okay. So, for each system call that is being given by the user, you have a routine in the operating system that needs to be invoked, and this routine in the operating system can take many parameters. So, those arguments or the parameters also should be given by the user as a part of the system call that he is using, and the parameters will be given, the routine is found out, the routine is executed, and finally, the return or the return values are being given back to the user. So, the system call interface invoke the intended system call in the OS kernel and return the status of the system call as well as any return values. So, here the caller need not know anything about how the system call is actually being implemented within the kernel. He just needs to obey the API, he needs to understand what should be the arguments given and call the OS, that is it. So, the details of the OS interface is hidden from the programmer. So, for that, say there are a number of operating systems in which they provide with an library routines like library routines which can be used by the user. Say look at this, you have an user application and in which there is an open system call. Okay. So, within the user's program there is a call open, and this open call will access the system call interface, and as I told you there is a system call table that is maintained in the kernel. So, for this open call from the system call interface he gets the corresponding number. As I told you, each system call has got a system call number. So, the system call interface will find out what is the number corresponding to this open call, and it will get this number and use it as an index into the system call table. So, from here it will get the address of the routine within the kernel which is to be executed. So, once it gets the address from here, the control will move on to the next to that particular address which is present within the kernel. So, this kernel has got, or the kernel means it is the operating system, it has got the implementation corresponding to this open call, and we need not really know what actually happens inside in this kernel. The kernel will execute whatever needs to be done, and generally if you look at this open system call, the return value will be a file descriptor. Say for example, you are trying to open a file, the return value will be a file descriptor. So, the file descriptor will be returned to this system call interface and that will be given to the user. And here you can see that we learnt about what user mode and kernel mode is. So, here you can see that when this application calls the system call open, immediately the system moves to the kernel mode because it has to access this kernel's code. So, it moves to the kernel mode, executes this, returns value and then it switches back to user mode and goes back to the application. So, this again shows it as a program. Say for example, you have a C program here where you have a printf statement. This printf statement is basically writing to the output device. So, this in turn, this is a printf statement which is provided as a library function, as a C's library function. So, this will call, in turn should call the system call write. So, when this printf is given, it will call the standard C library, the corresponding to printf there will be a routine in the C library which in turn will call write, the write system call. So, the write system call will be executed in the kernel, the returned value will be returned to the C library, which in turn will return back to the C program. Here again you see that there is a switch from the user mode to the kernel mode, and then again back from the kernel mode to the user mode. So, now here if you look at this program, this write is actually writing to the output device, and what is it writing? It is writing this string called greetings. So, this string or the parameter called greetings should be passed or should be told to this operating system as well, or it should be sent to this kernel code also. So, how is it sent from this user space to this kernel? So, there are different ways in which the parameters can be passed from here to the kernel. One is to have registers, that is the parameters are being put into registers and the kernel can access those registers and take the values from the registers. Sometimes say the registers are limited in number and you have limited size, and if the arguments that are being passed to the kernel is very large in size, then you can't write it to the registers and send to the kernel. So, then in that case you need to look at something else. What to do? You can have a block or a table in the memory where you can place all this full large chunk of data that you are passing as argument, and that data can be read by the kernel. But what you need to tell the kernel, you just say that this is the memory location in which the data is being placed, and that is being placed and that address is being placed inside a register. And this is the approach that is being used or done in Linux as well as Solaris. Now, the third option is that you can have the stack and the parameters can be pushed into the stack and popped off by the operating system. So, this block method or a memory table method as well as the stack method both do not need to have limited space. You can have as much space as possible. So, the length of the parameters can be very big in this case. And so, here you can see it is been shown as a diagram. So, you have parameters for the call, you place it into a memory space, and it is been present in memory address x, and this x, the address alone is placed in the register, and the system call that you are invoking is system call number 13, and corresponding to system call number 13 there is code in the operating system, and you call this and it will take this address from this register. It understands that from the register it understands that the parameters are present in address x, it will take that and it will use and then finish off its work. So, this is how you can pass parameters to system calls. And when you look at types of system calls, you have a number of system calls for process control, file management, device management, information maintenance, communications. For all these, say for all the functions that you have for the operating systems, you have corresponding system calls. So, if you look at process control, you have system calls for creating a process, for terminating a process, for loading a process, that is for loading a process into memory, for executing the process, and say if you want to end the process or if you want to abort the process, you have system calls. Very similarly, for getting process attributes, say for example, you need to know the ID of a process ID, or if you need to know the size of a process, or if you need to know about the details about a process, you can have system calls. So, you have system calls. So, you can get the attributes of a process, you can also set the attributes of a process, say for example, the parent of a process, the child of a process, etc., and so on. And then you can allocate space for a process, you can free space for a process, you can make the process wait for some amount of time, you can, that is you can suspend a process for some amount of time, then you can make the process wait for some particular event to happen. For all these you have corresponding system calls. And when you look at file management, you have system calls for creating a file, you have system calls for deleting files, you have system calls for opening, closing, for reading, writing. Say if you want to reposition, that is if you want to read from a particular position in a file, you can move the file pointer to that particular position, and for that you have system calls. And for getting file attributes, for setting file attributes, in the sense like you can know who is the owner of the file, when the file was created, when the file was last accessed, when the file was last modified, say when the file was actually created, etc., and so on. So, you have a number of system calls for different file attributes, for getting file attributes. Very similarly, you can set the file attributes as well. And then for device management, you have system calls for requesting for a particular device, releasing the device. Again, very similar to how you access files, you can also access devices. So, for that you have system calls for reading from a device, writing to a device, repositioning within the device, getting device attributes, setting device attributes. You can also logically attach and detach devices. Say for example, you can mount a USB drive, you can unmount it, or you can mount a hard drive and unmount it, and so on. You have system calls for all those. And then for information maintenance. So, you have seen number of calls corresponding to that now, that is you can have system calls for process, file, device attributes setting as well as getting all those information. You can set the date, time, you can set the date, time, etc., and so on. And then for communication, you have system calls for creation, deletion of communication connection. You can send, receive messages over the connection. So, if you look at this just shows a table of different system calls that have been used in Windows and Unix operating systems. So, for process control, fork is the system call that is used in Unix for creating a process, and when the process exits, it calls exit, and it can make the process wait for some amount of time or wait till an event occurs using the wait system call. And for file manipulation, you have system calls for opening, reading, writing, closing. So, open, read, write, close in Unix, and corresponding calls in Windows. And for device manipulation, ioctl, read, write, and corresponding here. And for information maintenance, this get PID is used to get the process ID of the current process, and this alarm is actually used to send a signal. Sleep is used to make the process wait for some amount of time or sleep for some amount of time. And look at this communication, you have this pipe system call which is used for inter-process communication, for communication between two processes that are related to each other. Say for example, a parent process and a child process can communicate between themselves. Communicate in the sense, send some information, send a string or something and receive a string or something, and so on. And then you have SHM get. This SHM get is actually used to create a shared memory. So, this SHM get system call is used to create a shared memory which can be used for communication between two processes. And very similarly, we have other system calls, say chmod can be used to change the permissions, the access permissions of files, and so on. So, we can see that there are a number of system calls that can be used for different operating systems. So, now having seen what system calls are, we will now move on to learn about the different operating system structures. So, initially this MS-DOS was the operating system that was written, and it was written to provide the most functionality in the least space. So, when it was written, the people who wrote this operating system did not really think that it will become a great success, and they did not divide that into modules. The OS was not divided into modules. So, it has some structure, but the interfaces, the functionality and all were not properly separated, and hence there were a lot of security problems also in this operating system. So, if you look at this MS-DOS layer structure, so you can see that there can be different resident programs, system programs, you can have application programs, device drivers, and you can see that all of these levels can access the lower level as well. There is no actual layering that is being done, and each level can access the other level as well, and even from the application program you can access the BIOS routines and so on, which was actually a problem which resulted in different issues related to MS-DOS. And this Unix system structure, it was initially limited by the hardware functionality, and hence this also had limited structuring. In the case of Unix, there are two separable parts. One is the system's programs, that is the different other programs that are present in the system in addition to the kernel. The kernel is the standard operating system. In addition to that, you have other system programs that are present in the system, like the compilers, etc., and so on. So, the kernel will have everything below the system call interface and above the physical hardware, and it provides the file subsystem, it provides different algorithms for CPU scheduling, different data structures and support for memory management and other operating system functions, and it has got a large number of functions, but it is considered as only one level, not multi levels, a single level with a lot of functionalities. So, this is the Unix system structure. So, here you can see that this is the actual kernel, this part, and below you have the hardware, and you have say device controllers, memory controllers, physical memory, etc., and so on, and between the users and the OS there is a system call interface, and the users can communicate to the system call interface using the shell, which is the command interpreter, and then within the kernel you have all the functionalities. So, you have a single layer, single level where you have all the functionalities of the operating system. So, operating systems functionalities like CPU scheduling, page replacement, memory management, file systems, IO systems, different signal handling capabilities, terminal handling capabilities, character IO system, terminal drivers, all these are being packed into the kernel, and then they came up with this layered approach. So, rather than having a single layer which will take care of everything, you have the layered approach where you have multiple layers and one layer is built above the other layer. So, for example, you can have n number of layers and each layer will have its own functionality. So, the advantage here is that you have modularity, okay, and the layers is selected such that each will use the functions and services of only lower level layers. So, a layer at level 0, if 0 is the lowest, it cannot make use of the functionalities of the upper layers. So, it is easier to debug, because say if there is some problem, if you need to debug, you can look into the lowest layer first, and if the lowest layer there is no problem, then you can leave off that particular layer and go to the next higher layer. The highest layer can be debugged next and so on. So, you can debug one layer after the other, and it is easier to debug, because you will not really find fault with say if there is no problem in a particular layer, say layer 2, then you do not have to worry about the lower layers as well if you have debugged all those. Okay. So, but the problem here is that when you say that you are going for a layering kind of model, it is difficult to clearly define what will go into each layer. So, the careful definition of the layers is important, and the interface between the different layers also have to be defined very clearly. Okay. So, say for example, so if you are the device driver for disk will be in a lower layer, and say if you are looking at memory management routines, they should be in a upper layer or a higher layer than this device driver routine, which is in a lower layer, because the memory management routine may have to access the devices. So, they will have to make use of device drivers. So, the device drivers should be in a lower layer than the memory management routine. So, in this way each of the functionalities have to be thought of and they have to define the functionalities accordingly for each of the layers. So, here you can see that an operating system layer will, a particular layer will have a number of operations, and if you need to bring in new operations into the operating system which will make use of these operations, then you need to bring in another layer which will sit above this and make use of these operations in this particular layer. So, this OS2 had operating system had this layered kind of structure where you have a device drivers in the lowermost, and then you have the kernel which will have the major OS routines like say memory management, task dispatching, device management and so on, and then above that will sit the different other subsystems, say IO subsystem etc., and so on, which in turn will make use of the functionalities that are present here, which in turn will make use of the underlying layer. And then above this you have the application programming interface, and you have applications that sit above this. We have seen in this class about different system calls, what system calls are, how they act as an interface between the user and the operating system, and what are the different types of system calls that are present, and what are the types of system calls that are present corresponding to different functionalities of the operating system. And then we learned about the different operating system structures that have been used. Thank you.